In this chapter, we are going to look at limiting factor analysis, and this involves techniques to help where there are scarce resources in a business. If there's just one scarce resource, such as a lack of skilled labour, then we look at single limiting factor. If there's more than one scarce resource, so there's also, for example, a lack of particular material, then we've got multiple limiting factors, and we have to use linear programming techniques. The whole idea behind all of these techniques is to decide on a suitable, the best, product mix for a particular business. There is a link here to the material that we covered in the throughput accounting chapter, because the bottleneck that we looked at there is actually a limiting factor. As you should be getting used to now in F5, what we're going to do is some techniques, some mathematical techniques in this case, and we're also going to look at the application, the benefits and the limitations. Questions will involve discussion as well as calculation.
So if you'd like to pause this presentation for a moment, just to take a couple of minutes to read through sections 1 to 3 in the talk notes. Okay, so if we have a quick look at the key things there from section 3, shadow price. It's the additional contribution from one more unit of your scarce resource, that limiting factor. So it's not if you had enough to make one more whole unit of production, if you had one more hour, one more kilo, how much extra contribution would that generate? Now, the way that questions are sometimes asked, the extra little requirements at the end of a limiting factor question, you could be asked how much extra you would pay for one more unit, what is the shadow price of that unit, or how much would you pay in total to gain one more unit of that limiting factor. Now just be careful with the wording, make sure you read them carefully. Your shadow price is the maximum extra that you'd pay for that additional hour, additional kilo. It is not the total amount. In order to get the total, you need to take that extra and add that on to the original cost per hour, cost per kilo that you were given in the question. So let's have a look at lecture example 1. If we have a look at the requirements, part A, we're asked what is our optimal production plan. Part B, what happens if we have 5 extra machine hours. And lastly, the shadow price of a machine hour. So have a quick look at the detail in the scenario. We've got a company, Jam and Sponge, which are making cakes, and they're struggling to cope with the increased demand. Machine time available 300 hours per week. We've then got our various selling price, cost information, machine time per batch, demand per week. Okay, so we have a limiting factor question here, single limiting factor. Likely that machine hours here are a problem for us. Now part A, the optimal production plan. This knowledge to get this far you would have seen before in your previous studies. Now remember, in order to deal with a single limiting factor, we need to get to contribution per unit of limiting factor. So let's remind ourselves of the approach that we would take for part A. Firstly, we need to determine whether or not machine time is indeed a limiting factor. If it is, we want to calculate the contribution per limiting factor. Now the way that we do that is we calculate contribution per unit first for each of our types of products. So in this case, the fairy, butterfly and pixie cakes. And then we need to divide that by our machine hours per unit. So per unit of fairy, butterfly or pixie cake. We can then rank the products in order of the highest contribution per limiting factor, and then we can allocate the hours available to those products to arrive at our optimal production plan. Now I suggest you pause your recording now and have a go at part A, and then we'll have a look at that and have a look at parts B and C together. Okay, so hopefully your answer to part A looks something like this. Start off by just confirming that machine hours are indeed a limiting factor. We get to our contribution per batch of cakes by taking the selling price less the variable costs, divide that by the hours per batch. We get to our contribution per hour. We can then rank those cakes and come up with our optimal production plan. So we would make 50 of pixie cakes and butterfly cakes. Fairy cakes, which ranked last, well, we've got 150 hours left to make those. We need 5 hours to make a fairy cake, so we can make 30 cakes. So our optimal production plan, 50, 50 and 30. Now part B, we are asked what would happen if we had 5 extra machine hours available. Well, if we had 5 more machine hours, there is no point making any more pixie or butterfly cakes because we've already fulfilled our maximum demand. So what we would do is make additional fairy cakes with those 5 hours. Now, given we need 5 hours to make a batch, we're going to make 1 more batch of fairy cakes. Now, part C asks us what is the shadow price of 1 more machine hour. Well, the shadow price is the extra contribution we get if we had 1 more machine hour. Now, as we've established, we would make another batch of fairy cakes. So what we're looking at here is the contribution that we would get from 1 more hour of fairy cakes. Now, we already worked that out, actually back up in part A. So $10 would be the shadow price, and that therefore would be our answer to part C. Okay, so let's have a look at section 4. Now this is looking at limiting factors with throughput accounting. Now what we saw in chapter 2E, that throughput accounting uses some terminology called return per hour. And return is focused on your sales less your material purchases only. So if we have a limiting factor scenario and we're in a throughput accounting environment, the only change that we see from that we've just looked at in example 1 is that we look to maximise our return per limiting factor instead of contribution per limiting factor. So let's have a look at example 2. We have a look at the requirements. Here we've got to prepare calculations to determine the production mix that will maximise our profit. So let's have a look at the scenario. It tells us we're in throughput accounting environment. We're guaranteed a weekly salary. So in case you missed that first line in the example there, the clue is in there that is telling you that that immediate labour bill cannot be altered. It is fixed in the short term. Now they're paid a rate of $7 an hour. Then got information about our batches. We're told our maximum demands. However, they don't include a contract for the delivery of 50 batches of each. If that contract is not satisfied, we have to pay a substantial penalty. Now, it doesn't matter what that penalty is. Basically, this question is telling you these demand numbers are not the only thing you need to make. You have to supply this customer. So I would annotate the question so that I don't miss that when I'm trying to look at how much material, etc. is needed. And basically, these here should be fulfilled first. So regardless of the priority, for the rest of the production, we have to satisfy this first. Material L, short supply, maximum amount available, 7,000 kilos. Now, if you fancy having a go at this on your own, following the approach that we took for lecture example 1, but just using return, not contribution, then if you'd like to pause the presentation to have a go, and then you can have a look at the answer. For those of you that want to work through it, I'll run through that now. So first thing that I'll do is check whether we have enough of material L. So I'll bring in my 3 products. I'll look at the amount that I need to supply. So we've added those 50 batches onto each. So I've got to do 550, 450 and 400. So if I bring in the kilos of L required per batch. Now what you can see from the question is it doesn't tell us how many kilos, it gives that to you in dollars, but we know that each kilo costs us $10, so it just needs to do a quick calculation to find out the amount of kilos required. So we need 7, 9 and 4. So kilos of L required in total. So if we total those up, we can see that we need 9,500 kilos. We've only got 7,000 kilos available, so clearly we have a limiting factor. So let's have a look at how our products should be prioritised. So we need to calculate our return per batch initially. So if I bring in my 3 products again, I'm going to bring in my selling price, and then what I have to do is deduct my material cost. Remember, they're the only variable cost in the short term under throughput accounting. Let's bring in those selling prices and then bring in the cost of the material. So I'm just going to add up those 3 items. And give me my return per batch. So I haven't got my return per batch. I want to get to my return per kilo of material L. So let's bring in kilos of L per batch. So we had 7, 9 and 4. So I'm going to take my 90 divided by 7, etc., for each of those products. So return that we get per kilo so I therefore made Luke first, then James, and lastly Adam. So that's my priority. What I now need to do is draw up my optimal production plan. So I'm going to bring in my units. I'll bring in my kilos per unit, and then I can get to my kilos of L. Now we know initially that we have 7,000 kilos. Now remember, before we apply our ranking, we've got to deal with that contract first of all. So for each of them, so for Adam, I'm going to do 50. For James, I will do 50. And for Luke, I will do 50. So in terms of kilos per unit, Adam, we had 7, James was 9, Luke was 4. So let's see how much material we have left once we have applied the contract. That leaves us with 6,000 kilos available. So I can now apply my ranking. So I'm then going to make Luke And the demand for Luke was 350 batches. We needed 4 kilos for each, so we need 1400 kilos for Luke. And that leaves us with 4,600 kilos. So we'll start production of James. We would like to make 50 batches, we would like to make 400 batches of James. It's 9 kilos, so that is going to take 3,600 of our kilos, leaving us with just 1,000 kilos, which will go on production of Adam. Now Adam needs 7 kilos to make a unit. So with his 7 kilos, we need to work out how many he can make with 1,000 available, and basically that works out at just over 142. So he'll be able to make 142 batches of Adam. Okay, so let's have a look at linear programming then, technique we use when we have more than one limiting factor. Now you can see from the notes here, and those of you that can remember back to F2 will remember that it's a very step-by-step approach that you need to take. Majority of the time in F5 you will probably be asked to formulate the model and solve the problem. It is possible that you could just be asked to formulate the model, however, and that is just those first 3 steps there. Now the first step, define the variables. Basically your variables are your products. Okay, now you're never going to have more than 2. Any more than 2 you need a piece of software to solve it, so we're only going to be looking at 2 products. We've got to establish our constraints, formulate our objective function, and that is going to be to maximise contribution or profit the majority of the time. Even if the question talks about maximising profits, remember your fixed costs don't change regardless of the level of volume, so you can still do your calculations here on the basis of contribution. Even if at the end you have to give a profit number, you just need to remember to knock off your fixed costs from your final calculation. Here you've then got the other steps to carry on and solve the problem. Best way to do this is really to do it through an example with you. Okay, so let's have a look at example 3. We've got to determine our optimal production plan and calculate the contribution that we can achieve. You can see here that we've got 2 products, purse and the handbag. Purse earns $5 contribution, the handbag earns $6. We've then got our leather and our labour. Now in terms of the labour that's available, we have 6 skilled labourers, each working a 35-hour week, so we have 210 hours available. In terms of leather, maximum of 600. We've also then got an EU quota. We have to produce at least as many handbags as purses. Okay, so first step then is to identify our variables, and remember those are your products. So all we're going to say here is let P be our number of purses and let H be our number of handbags. Okay, if we formulate the objective function, what we want to do here is maximise our contribution. And we're told in the question that the purse earns $5 of contribution. So our contribution will be 5 times however many purses we make, and it will be $6 times however many handbags we make. We then got to deal with our constraints. So these are all of the items that are restricting us in some way. So let's have a look first of all at a leather. The question tells us that we need 1.5 meters to make a purse. So we've got 1.5 times however many purses we make. And we need 2 meters to make a handbag. So 2 meters times however many handbags we make. And that has to be less than or equal to the 600 meters that we have available. If we go through the same process for our labour, we're told that we need 45 minutes, so that's 3/4 of an hour to make a purse. We need half an hour to make a handbag, and that has to be less than or equal to the 210 hours we have available. Now the other quota that we have there is an EU quota, and that says that we have to make at least as many handbags as we do purses, so H have to be more than or equal to the number of purses that we make. So it's a very typical set of constraints. Other than the quota, slightly unusual there, what you'd often have here instead is a maximum amount of demand for H or a minimum amount of demand. So you would just be stating that H has to be less than or equal to or greater than whatever those numbers are that you're given. Now, in addition to the constraints that you have in the question, remember there's always one other that you need to bring in, and that is for non-negativity. So basically, we want the outcome to give us purses or handbags which are either greater than or equal to 0. It's no good telling us we need to make -2 handbags, for example. Okay, now those 3 steps, that's our model formulated. So if we want to think about solving the problem, we need to think about doing this graphically. So we're going to think about getting some lines on those graphs. Now remember, to get a line onto a graph, we need to be able to work out 2 points, and then we can plot that graph. So the way that we're going to do this, we're going to have a line on our graph for every single constraint other than the non-negativity. The non-negativity is essentially already going to be there because we're only going to plot positive axes. Okay, so you've got a template that you can use here in your workings, but let's deal with the constraints. Now if we take leather, first of all, just going to bring in that constraint formulae again for us. So it was 1.5p plus 2 times h, and that had to be less than or equal to 600 meters. So what I'm going to say is, okay, well, let's assume that we don't make any purses. How many handbags could I make with that material? Well, then I'd have 2h being equal to 600, so I would therefore be able to make 300 handbags. If, on the other hand, I said, well, okay, let's not make any handbags, how many purses can I make? Well, I need 1.5 meters for every purse, so I would therefore be able to make 400 purses. Now this gives us our 2 points that we need to get our leather constraint onto our graph. Okay, so let's have a go at plotting that. So when P is nothing, handbags are going to be 300, and when handbags are nothing, purses are going to be 400. Okay, so 0, 300, 0, 400. So link up those 2 points, and that is your leather line. Now it's important you don't take any shortcuts, cut any corners here. Make sure everything is labelled properly. There will be marks going for every aspect on your graph. You will lose marks if you don't have a heading for a row, a constraint, etc. Okay, so that's leather. Let's have a look at labour then. Same kind of process. Now, the constraint for labour was 0.75p plus 0.5h had to be less than or equal to 210. So let's assume we don't make any purses. We would therefore be able to make 420 handbags. So there's one of our points for this line. If we don't make any handbags, we could make 280 purses. So that's the other point for our line here. Okay, so for labour we've got 280 and 420. So join those two up. And that gives us there a labour line. Okay, so there are constraints for leather and labour. The only other constraint that we need to catch on here is the one for the quota. Now the quota said that we need to produce at least as many handbags as purses. The way we're going to get this line on the graph is to take it from the origin, going up at a 45-degree angle. It will always give us the same amount then of purses and handbags. Okay, now that is our quota. So we've now got a line on our graph for each of our constraints. What we're then able to do is identify the area in which we're able to produce. Okay, now what you'll find is you tend to have a little shape sort of nestled inside of your constraint. So basically you have enough of everything to be able to produce in that area. So in this particular example, we've got this sort of triangular shape here. And we can produce anywhere in here with the constraints that we have been given. Okay, now this area here is known as a feasible region. What we need to work out is at which point in that feasible region are we going to maximise our contribution. Now if you look here, we could produce 100 purses, 100 handbags. That would give us an amount of contribution, but if we were to produce, let's say, 200 handbags and 100 purses, obviously that's going to give us more. So what we want to do is to be able to produce as far over at the outer limits of these constraints as we can in order to maximise our contribution. Now basically that is going to be at one of these points, either 0, obviously no contribution though, here, here and here. So I'm just going to label those A, B and C. Basically those are the outer limits of our area, and it's wherever two of our constraints intersect. Now they are going to be the points that maximise our contribution for us. What we've got to do is work out which. Now there are various ways you could do that. If you wanted to, you could just read off the graph how many handbags and purses we're making at each of those points, multiply them by the contribution per unit, and that would then tell us how much contribution we're making. We can choose the best point. Now that method would gain you marks, okay, but it's not the preferred method of your examiner. So the approach I'm going to show you now is the one that he prefers and the one that would gain you most marks in the exam. Now what we want to put onto our graph in order to understand that optimal point is what we call an ISO contribution line. It's a line which shows us the correct gradient that will maximise our contribution. The way that we work out where this line should be is we bring in our objective function. Now we said that we maximise contribution when we had 5p and 6h. Now you can adopt an approach very similar to that we used when we dealt with our constraint lines and getting those lines on the graph. So in other words, we'll say we don't make any purses, how much contribution will we get from our handbags, and vice versa. In order to do that, obviously we need this equation to equal something. So all I'm going to do here is always multiply my two values together here. Now 5 times 6 is 30. And that is what I'm going to use to solve this equation. So I'm going to say let my purses be nothing. 6 times h is 30. How many handbags would I need to make? I would need to make 5. If I didn't make any handbags, 5 times p is 30. I would therefore need to make 6 purses. Now what you can probably see here is that the numbers have switched places. Contribution formerly was 5p and 6h, and now I'm saying that h is 5 and that p is 6 if we make nothing of the other product. So rather than going through this approach, if you're happy with that, you can just sort of take your objective function formulae and just sort of switch those values in order to get your points that you're going to need for your line on the graph. Now the only problem here with 5 and 6 is that these are obviously too small to use accurately in terms of the scale we've got on our graph. So if you've done this and you end up with numbers which aren't appropriate, you just need to make a scale adjustment. Now all you need to do is multiply by 10 or 100, or divide by 10 or 100 and 1000 to get your appropriate scale. Now here each of my squares are worth 20, so I'm just going to multiply by 10 here. So h would be 50, p would be 60. So let's drop that line onto our graph. Now be careful when you do this, what you want to put on here is a dotted line rather than a solid line. Okay, so our ICA contribution line, we want 50 handbags, which is here, and we want 60 purses. So remember, we're going to join these two lines with a dotted line, and we're always going to label everything we put on our graph. Here's our ISO contribution line. Okay, remember, it's important not to cut corners when you're doing your graph. Everything on there will get marked. The presentation, the labels of the axes, the label of the constraints, each one of those will be gaining you probably half a mark for each. So make sure you don't leave any of those out. Now this ISO contribution line clearly isn't the point at which we're going to maximise our contribution, but it gives us the appropriate gradient. So what we need to do is basically take this line and push it out in parallel, so keeping the gradient the same, as far as we can until we leave our feasible region. So by keep moving it over in parallel, we'll see which of these points, A, B or C, is the last to sort of be reached, and therefore the one which will make the most contribution for us. Now when you do that, what you should find is that B is the very last point remaining. A goes first, then C, then B. Now if you're not getting point B, it could be that your squares aren't perfectly square. If that's the case, redo your graph on proper graph paper. Okay, in the exam, graph paper will always be available, so make sure you ask for it. If you use something that's not perfectly square, you can produce a different optimal point. Okay, now B we've identified as our optimal point, so again I'm going to annotate that on my diagram. Now, having identified B, I can read off of my graph here. It's at a fairly clear intersection. It looks like we should be making 180 handbags, 160 purses. So I can take that and multiply that by the contribution of $6 for a handbag, 5 for a purse, to get to my contribution. I might not be too sure whether I've got that perfectly right, so I might want to check it, and I can do that using simultaneous equations. Now the other way of doing this, instead of using your ICA contribution line, is to actually do simultaneous equations for each of our points A, B and C. Okay. Now again, it's not going to get you as many marks as doing the ICA contribution line. It can be quite time consuming. So I wouldn't recommend doing this approach if you've been asked to draw the graph. However, I would recommend doing it just to check your answer. Now our next lecture example looks at the use of simultaneous equations. So we'll have a look at proving that and working out our contribution for this one here in lecture example 4. So example 4 asks us to solve the problem that we've just done using simultaneous equations. Let's just have a go at doing the simultaneous equations for our optimal point, which was for where our two lines, leather and labour, intersected. Okay, so leather and labour. So we need to bring in those two formulae. So we had 1.5p and 2h being equal to 600, 0.75p and 0.5h being equal to 210. Now lots of people don't like simultaneous equations, so I'm just going to mark up the steps as we go. Basically we need to have something that's the same on both of these formulae to be able to solve the values here. So what I'm going to do, I'll label these two up, 1 and 2. If I was to multiply my second formulae here by 2, I would have 1.5p in both 1 and 2. Now obviously you could choose to do it slightly differently. You could multiply 2 by 4 because then you'd have 2h in both 1 and 2. It doesn't matter which way around you do it. So we're going to multiply 2 by 2. And that's going to give us our third little equation. So 1.5p plus what would then be 1h would then be equal to 420. So I can now deduct 3 from my first equation there. What I'm left with is no p. I am left with 1h, and that is equal to 180. Now I know the value for h, I can drop that into my formulae and work out the value for p. So if I substitute, I'm looking at h into 1. So my first calculation, first formula there, 1.5p plus 2 times h, well 2 times 180 is 360, and that has to be equal to 600. So 1.5p is therefore equal to 240. So p is going to be 160. Okay, so my optimal production plan is to make 180 handbags, 160 purses. So just have a look at your graph that you did in our previous example, see how that compares. Hopefully it looks about right. As I say, it will just depend on whether the grid you've used to do it has perfect squares or not. In the exam, you'll always be provided with graph paper. Make sure you ask for it if you don't get given it automatically if you need it, because you can draw wrong conclusions without it. Having got those, obviously if you had to go and solve your problem in this manner, you just multiply it by your 5 and your $6 for your contribution to get to a final contribution value. Just capture our contribution. Handbags and $6, purses and $5. So 1880 would be our resulting contribution. Okay, so make sure you're familiar with these definitions here, slack and surplus, likely to come into a question on linear programming because it wasn't in F2. So make sure you can describe each of those two terms. So slack is any spare material. We didn't use all of our limitations. Surplus is when we make more units than we had to. Now lecture example 5 deals with these two and also shadow prices, which is the other element that your examiner is likely to introduce at F5. So what we'll do is use the data from example 3 to calculate these values. Now what we got to in our previous example is an optimal plan of 160 purses and 180 handbags. Now if you look back to example 3, you can see the amount of leather and labour that was needed for each. So first of all, let's look at leather. We needed 1.5 meters for a purse. We needed 2 meters for a handbag. Now what that takes us to is 600. We had 600 meters of leather available, so therefore there is no slack leather. Same thing for labour. For labour we needed 3/4 of an hour for our purse. We needed half an hour for our handbags. Now that takes us to 210, which again is exactly the amount of hours we had available, so therefore there is no slack labour either. Now you would expect that, given our optimal point was where leather and labour crossed, there was no spare, we were using everything we had. If we'd have had an optimal point which was, let's say, labour and the quota, we'd have probably found that we had some slack leather. Now if we have a look at shadow prices, this asks us to do it for materials and for labour. Now you have to do them separately, you can't combine them. And basically remember, shadow price is the extra contribution from one more unit of limiting factor. So the way that we can work out a shadow price when we've got linear programming is to bring in the constraints at the optimal point but add one more unit of one of those items. So let's have a look at materials, which in our case was leather. If we bring in our constraints again, we have 1.5p plus 2h being equal to 600. Well, I want to work out my contribution for one more unit, so I'm going to make that be equal to 601. I'm going to keep my labour constraint exactly as it was though, and then I'm going to solve this equation in the same way as we did in example 4. Now it's very important when you're calculating shadow prices that you keep the decimal places in. We're only bringing in one more metre in this case. It's not enough to make a whole unit. So in order to calculate the extra contribution that this generates, we need to work in part units, so keep as many decimal places in, otherwise you won't get any extra contribution at all. So let's work out the contribution we get from our new optimal production plan, which is 181 lots of H and 159.33 hearses. So contribution. Our handbags generated $6. Purses generated $5. 1086 and 79665, and that gives us 1882.65 of contribution. Now our previous contribution was 1880, so the extra contribution, and therefore our shadow price is $2.65. Now the question asks us what that meant for kg. Well, that is therefore the extra that kg would be prepared to pay for 1 more metre of leather. Now if you were to go back to lecture example 3 and the initial detail that we got, you'd see that the usual price for leather was $8. So if we bring in the extra and the 8, you would see there that $10.65 is the maximum that we would pay for any extra leather. Okay. Now that's the process you need to go through. So have a go now at calculating the shadow price for the labour. Just remember here that this time you need to put that back to 600, and this time we're going to have 211 hours available. Okay, so what you should come up with when you work out your shadow price for labour is extra contribution of 135. Okay, so that's your shadow price, and what does that mean for kg? Well, they would be prepared to pay up to $5.55 for extra hour of labour. So if we summarise then what chapter 3 contains for us on limiting factors, basically you could have to deal with a question focusing on single limiting factors or multiple limiting factors. Single limiting factor questions, you're going to be asked to solve those by looking at the amount of contribution per limiting factor and prioritising those products with the highest, or potentially return per limiting factor if we're in a throughput accounting environment. Other thing that you could be asked to calculate here is your shadow price. Remember, your shadow price is the additional contribution that you get if you have 1 more unit of limiting factor. So on a single limiting factor scenario, you can take that contribution per limiting factor you already worked out. With linear programming, got several constraints, but you're only going to have 2 products, and remember they are your variables. You need to solve the problem, probably using graphs. Remember to get your ISO contribution line on that graph in order to find your optimal point, and then you can use simultaneous equations to just double check that you've read the appropriate point on the graph. If you've got to calculate a shadow price here, remember take the simultaneous equations for those two lines that intersect at your optimal point, increase whichever one you're looking at by one amount, and then solve that problem, work out your new optimal production plan and your new level of contribution. The extra is your shadow price. Remember not to do both at the same time. If you have to do that, you need to do them individually. Other things you might be asked to calculate are your slack and your surplus. So remember, slack is when you've got some resource left over at the end. Surplus is when you've made more output than that minimum requirement.